All right, everybody, we're going to do Module 13, OYOs. So 13.1, and we're supposed to balance equations and then include the energy. So the formation of ammonium nitrate has a delta H of negative 365.1. So we have to figure out what ammonium nitrate looks like. And when you look it up, it has NH4. That's from clear back in a few chapters ago or modules ago. Ammonium is a complete polyatomic thing, and then nitrate similarly. Formation here. And so we have to separate all the parts. So we have N plus H plus O. And we also know that all of these guys are homonuclear diatomic, so they all have to be here. They've got to have their 2s. And we know that it's going to make NH4, NO3. We've got to balance all of this, right? Here's what I also know. It has a delta H. So, and according to our book, if it has a negative, it's exothermic. So I need to put 365.1 K on 0.1 K on this side. Okay. So now I've got to work this through and make sure that I have my equation in balance. And I've got an N2 here, so I'm going to just go ahead and put a 2 there. And as I have to make this, put this 2 in because I have this as an odd number, and I've got to make it so that it can work with even numbers. So now I'm really ready to balance it more directly. And 2 n's times 2, so there's my 2n2, H4, that's pretty direct, and 2 O3s. If I put 3 here, that will give me my 2 N2, 2 H2, 3 O2 will make 2 NH4, NO3 minus 360, or I'm sorry, it should be a plus, 365.1 kilojoules. All right, let's do another one, 13.2. So the decomposition of manganese oxide, so manganese oxide, and this is 4, so we know it's manganese oxide, which has a delta H of 519.7, so we know that's a plus. So manganese oxide is decomposition, so decom, so we know what we're doing there. So we have to break it down. According to the book, the manganese is in the transition metals. Of this, it tells us that it's manganese is a 4+, right? If we look up O2, we know that O is a 2-. Okay, so when we look, there's your 2 that's minus, so 2-. And then manganese is in the transition metals, and they have to be told what those are. We have to cross and drop to make that actual item. So it's MN2O4. But look at those. Those can be reduced. So it's MnO2. Okay, so that's what we're trying to decompose. So we have MnO2, and in this case, we know that this is a positive amount of energy, so that it's drawing that energy in. So we can say 519.7 kilojoules. And as it breaks down, it's Mn plus O2. Now, is that, are we balanced? Yeah, because Mn and O2 are the same on both sides, and we don't have to worry about our energy. 0.1C. So the reaction between H2CO3 and KOH, which releases, so since it releases, it's a minus, right? So 21 kilocals. In this particular case, K is 1+, CO3 is a 2-, so that's going to be important to be able to solve for this. We know that, so if we have H2CO3 plus KOH equals, and so I have to rearrange them, right? So we have K2, so we rearrange these, it's K2, cross and drop, CO3, we don't have to do anything else with that, plus, and it's H2O, so we have this guy and this guy, so H2O, plus our 21 kilocals. All right, so we've got, that looks pretty good. Now we have to make sure it's balanced to here. And that takes care of this. Our K is 2, our K is 2. Our C's can be left alone, and our O3s. And then we have an extra H2O, so we have to add our 2 here to make our extra H2O, because we have 2 OHs and 2 H2s here, right? So that gives us our balanced equation there. All right, and that means it's exothermic because it's a negative and it lands on the product side. Carbon tetrachloride is widely used as an industrial solvent. What is the delta H of the formation reaction? So carbon tetrachloride. All right, so we know that carbon is C, tetra is 4, chloride is Cl. So it's carbon tetrachloride. That's what we're looking at. All right, and it wants to know the formation. So we have the formation of it, and it wants to look at the delta H. So we have to take our carbon and tetrachloride. So we have C plus Cl. Now we know that Cl is one of the homonuclear diatomic, so it has to have a 2 beside it. We make it into CCl4. All we have to do is add that 2 there, and we've got it solved. Table, and can you see that I xeroxed my table and cut it out so that I can easily reference them. Currently I'm going to be using the top table number 13.2, because it's asking for bond energies. So what I have to do is just simply take my my bond energies and look them up and write them down. Okay, so in bond energies, the single atom it's not formed, it's not a problem, so it's a 0. So all I have to do is I kind of do it in order, right? So I have Cl2, and I can look that up, Cl to Cl, right here it is. See, there it is. It's 240. So 2 times 240, and this is kilojoules, right? And actually, this is like 2 moles. We can get rid of that. 2 moles times 200 kilojoules per mole, and so I can get rid of the moles here. And then I'm going to subtract the CCl4. So C to Cl is 327. So I can do, that's horrible, right? 327 times 4. And I can multiply that out. 480 kilojoules, that's what this is. And 1308, this. And when I subtract it out, I get minus 828 kilojoules. And they say minus 830. All right, so we're just looking up those energies, the bond energies, and adding and subtracting them. In an acetylene torch, C2H2 is burned to make the hot blue flame that cuts or welds metal. Assuming that the combustion is complete, what's the delta H of this reaction? All right, so acetylene torch, C2H2. So we work with C2H2. And we know that if it's going to be a complete combustion, we add oxygen and we get CO2 plus H2O. Okay, and these are all gas. So we have a gas here, and I'm assuming this is balanced. This has to be a 4 because this is a 2 times 2. This is 2. All right, so this becomes 4 now. And then this is 4 times 2 is 8. And that makes this a 10. So now we have 5. So our balanced equation is 2 C2H2, 5 O2, and 4 CO2, and 2 H2O. So we're going to get rid of all that. And now we can go ahead and find our bond energies. So this is where they want you to actually start drawing them. All right. So we had to use our Lewis structures to determine what that looked like, what this shape of the molecule looked like. So we had to actually build them. So here we have our C's connected, and then our H's come off the C's. So we had to account for the C connections, the C bonds, and the H to C bonds. So when we have all of those put down, now we're just simply going to multiply all of those and subtract. We're presuming that you're understanding that these are moles here, and then this is kilojoules per mole, and so the moles go away. All right, so that we're keeping mathematically, we have our mathematical integrity, as it were. Okay, so I've written this out. Let's see if I can get them put in some order. I have 1670, that comes from this guy, plus 1644, that comes from this guy, plus 2470, that comes from this guy. This becomes a minus, so we're going to just go ahead and multiply that out. It's 6392, that's this guy. And we're subtracting also 1836, so that's from this guy, right? And we, when we're done with that, we get 5784 kilojoules minus 8220 kilojoules. Now, if you're doing this off of your calculator, you would just go plus, this plus this plus this minus this minus this, and you'd get one total, which is minus 2436 kilojoules. And so the delta H is that, and it is exothermic because of this. It's an exothermic reaction, and that is obvious because it's an explosion. When you ignite anything, you're going to get heat, and so we should have gotten a negative here. It would have been a problem if we didn't. When you use a cigarette lighter, hopefully not to light cigarettes, you're burning gaseous butane, so C4H10. Assuming it's a complete combustion, what's the delta H for this reaction? Do not use bond energies to solve this problem. Use Hess's law. All right. Well, at this point, we still have to go ahead and do our thing. So we know it's we add oxygen, and we get carbon dioxide plus water vapor, right? So now we have to figure out do we have, how can we balance our equation? This is is 1. This has to be 2, so we have to make this into a even number. This H is 10, so in order to do that, I have to have a 5 here. Nope, I have to have a 10 here. So by making this 10, that makes this even. So we have CHO, CHO. So now when I do that, currently I have C as 4, H as 10, O as 2, C as 1. We'll fix that quickly. H was 2, but now it's 20. And now C was 1, but now it's 10. All right, now we go back to here. If this is 20 here, then we have to automatically correct for that. So that puts that at a 2. That makes that 20. 2 times 4 is 8. And we leave the O2 alone. So now we have to correct for this, and that makes that an 8. So this is an 8. Now now we can deal with our oxygen. So 2 times 4 is 16. We already know that 10 times 1 is 10. So we get 26 here. which means we have to change this to 13. Okay, so that is our formula or our equation, and it's balanced. So we can go ahead and work through Hess's law. So now when we look at Hess's law, we have to go backwards, right? So our law per se is delta H equals the sum of delta H products minus the sum of delta H reactants. So we've got to reverse this. So we're going to take these guys here. Let me get a different color so it maybe can be more clear. We're going to get these folks here, and we're going to put them first, and we're going to subtract them from these folks here. Okay? So I have 8 of them, and we're dealing with kilojoules per mole, so we can use our stoichiometric coefficients and get rid of the moles. So 8 moles times, and we said this was negative 394 kilojoules per mole. Okay, so we know that we're going to get rid of our moles. That's not a very good, it's not a very clear one to use, is it? Let's use our brown. It seems like it's a little finer. Okay, so we're going to multiply those together, and we're going to add them with this guy. So we have 10. And H2O we're using gas, right? Because it's a combustion. We're at the other end of the combustion, times negative 242. And then we're going to subtract. So we're going to keep the thing going because we're having trouble keeping it all in one line. And is minus 126. Minus 126. 126. And we are going to go ahead and subtract because it's a continuing minus 13 O2s. And with Hess's law, we don't have to deal with O2 because it's a formation. It's an originally formed molecule. All right, so now if we multiply this out, I'm going to go ahead and do it here. We get minus 3152 kilojoules minus, because this is a minus 2, see? Minus 2420 kilojoules. And now this is subtracting this. So this subtracting this, it makes this a plus, right? So we have plus 252 kilojoules minus 0, right? So because it doesn't matter, we really can get rid of that one. But notice we have a negative here and a negative here, and those two negatives cancel each other out and make a positive. So that's so we get, if we add these two together, 5572 plus our 252, and we end up with minus 5320 kilojoules. And they said 5.320, I think, times 10 to the third kilojoules. Okay, to make seashells that house and protect them, many shellfish take solid lime, so we're taking CaO from the ocean floor and react it with gaseous carbon. We got to carry about. They're giving us hints. And they react it with gaseous carbon dioxide, CO2. Okay, gaseous, we know that. That's been exhaled by marine organisms. The resulting calcium carbonate, and we know that that is CaCO3, and is a major component of their shell. We know that it's a solid. All right, and then they want to know what the delta H is. All right, first of all, we have to make sure we have everything. CaO, 3 O's, and C. Hey, it's already, that's kind of them to give it to us for that. Remember, we know our delta H is the sum of the delta H for the products minus the sum of the delta H of the reactants. So we're going to make sure that we've got our CaCO3 goes this way, and then subtract it this way, right? If we go to our chart, CaCO3 is here, it's a solid. So we have 1 mole of CaCO3. We multiply it by our negative 1207, and that's kilojoules over moles. So we know that we're going to get rid of all the moles. I'm not going to do that I'm not going to keep doing that just because it's going to mess up. It makes everything a little bit messier for me. All right, we're on our reactant side. We have CaO, which is a solid, so we have minus 635. I guess if we were trying to help us with our math, it'd be 1 times minus 635 because we have 1 mole there. And we're also subtracting the CO2, which is a gas, and we have 1 minus the 3 CO2 at 394. All right, so now we can just go ahead and figure our signs and how it looks. So since these are all ones, we don't have to, we're just working with signs. We have negative 1207 kilojoules minus, so this becomes a plus 635 kilojoules. And this, because this is a minus, this becomes a plus 394 kilojoules. All right. And when you add those all together, you get a minus 178 kilojoules. All right. That's our answer. 13.6 ethane gas, which is C2H6, has been considered as a fuel for automobiles because, like octane, it releases a lot of energy when it's burned. How many kilojoules of energy are released when 500 grams of ethane undergo complete combustion? Anything plus oxygen. If we're looking for a combustion scenario, then we get CO2 plus H2O. We know these are all gas because they're burning, right? We really have to deal with the gas. And then we also know there's a delta H, so we can go ahead and put that in there. We're going to look for the delta H, right? So we're going to try to find what that is. And then we have ethane. So we actually are going to have to go back and find out what is the energy pull when it's 500 grams. So we have to use stoichiometry for this. And when I look at it, it looks as though our C2, so we're going to have to do something with our C's, but we better start with the O's because this is 2 and this is 1. So C, we have a 6 here. We need to at least put a 3 here. No, we can't because this is that's an odd number. So we're going to have to put a 6 here. So if we have 6 H2s over here, then if we've got 12 over here, we have to make a 12 over here. So that automatically makes that a 2. So now this is 12. 2 times C is 4. That makes this a 4 here, right? So C2 times 2 is 4. Now we have 4 C's over here. And now we're just going to have to figure out how much our O's have to be. So if we have 4 times 2 is 8, and plus 6, that is 14. Is that right? And so that makes this 7. Equals the sum of our delta H from the products minus delta H of the reactants. So we're going to these have to go this way. We have these guys here minus these guys here. Using this guy here, so our CO2, we have 4 of them. And remember, we do 4 moles times our CO2, which is minus 394, and that's kilojoules over moles. And so we're going to get rid of all of the moles by just doing that, right? We can add this, which is H2O, and I think we have an H2O gas. So that's one of the reasons why we needed to know it was a gas, minus 242. So we have 6 of those times minus 242. And now we're going to start subtracting properly. We have our C2H6, which is a gas, and that looks like negative 84.7. So we have 2 times negative 84.7. And the O2s does not have any energy because it comes that way. So since it comes that way, we're not looking for energy from that. All right, but we could say minus 0 if we wanted to, just to keep track of all of our parts. So, all right, so then we go ahead and multiply that out, and we get minus 1576 kilojoules plus a minus 1452 and minus a minus 169.4. Right? So we figure that out as minus 1576 minus 1452 plus 169.4, and we get a total of negative 2859 kilojoules. Okay, now you'd say, well, is that the answer, Joe? No, that's not the answer. This just tells us that we have the amount of energy for this thing, for this one reaction, right? But the problem is we're not asked about that reaction. We're asked if there's 500 grams. So we have to figure out how many moles are in 500 grams. So now we have to do our AMU. So we get a total of 30.1 is our AMU. And it's also grams in 1 mole, 2 moles. We have 500 grams. So we're trying to move from grams to moles. So 500 grams of C2H6, that's our sample. We've got to convert it from this, our ratio here. Our grams go on the bottom, remember? It's 30.1 grams in 1 mole. So now we can get rid of our grams out, and we just divide it up, and we get 16.6 moles that were used. Now, here's the thing. We have a ratio. We have 2 moles of C2H6 makes this amount of energy, but we have this amount of moles. So we're going to have to do another simple comparison conversion. That many moles of C2H6, that's our sample. And we're going to say energy right here so we know what we're doing. And we're going to compare it to our ratio of 2 moles to our energy. 2 moles, and it is 2859 of our kilojoules. So if we get rid of that, divide it and multiply, we end up with 3.4, so that's 2.37. That's where we get that, and then 10 to the 4th. All right. Okay, let me set this other one up, and then I'll bring you in, okay? Okay, so this is 13.7. When mined, coal becomes contains a small amount of sulfur. When that coal is burned in a power plant, the sulfur burns right along with it, producing SO3 gas. So this is what we're at. When the SO3 gas reacts with the water in the air, it produces sulfuric acid according to the following reaction. So SO3 plus H2O equals H2SO4, which is a liquid. The sulfuric acid produced in this manner falls to earth as acid rain. So this is our acid rain right here. How much energy is produced when 25 grams of H2SO4, so this is 25 grams, are produced in this way? And we want to know what is the delta H. Numbers here, H2SO4. H2SO4, as long as it's a liquid, is negative 814, and it is, and there's no stoichiometric coefficient. So we're going to put a 1 there because that helps us remember that we're getting rid of the moles in the formula so that the integrity of the math stays, right? So I have a minus 814 kilojoules minus a minus 242 kilojoules, and this should be a minus a minus 396 kilojoules. And when I add them all together, I get a minus 176 kilojoules. All right, so I can go ahead and put this 176 kilojoules, and I put it back up here so I can keep track of what I'm doing, because I'm going to have to convert because I've got this little guy right here. So since I'm going to be working with this guy, I need to have some a bit of comparison. So I'm going to have to work with that. All right, so now since we are working in grams, we got to get out of grams. Obviously, we have to do the AMU of H2SO4. We get 98 AMU, which means 98 grams in 1 mole. 25 grams of H2SO4. That's our sample. And we're going to get out of grams by saying 98 grams in 1 mole. So we can get out of that. And we should get 0.255 moles used. Or made in this case. It was made, huh? So we have that amount. Now here's the thing. They want to know how much energy, how much delta H occurred. Have to take care of this and this, and we've got to compare it. We've got to use it as a ratio, because we know for every one H2SO4 molecule that was made, there was this amount of energy expended. So we're going to use this as a ratio to find out, or a conversion in a sense, to get out of here to show us how much energy was expended when only this much of H2SO4 was made. So H2SO4. All right, and we're going to get out of our moles. So we want to put the moles on the bottom. 1 mole of H2SO4 and it made that much energy. Okay, so we just multiply that out. 0.255 times 176, and we get 44.9 kilojoules produced in the sample. All right, that's the answer. Maybe you're gonna have trouble seeing it, but I can redraw it. So we have drawn energy diagram. So this action is hard to get started, or hard to start, but it gets very, very hot once it does. Ending of the reaction minus the beginning. That's how we know, right? So we have to take our ending here minus the beginning. If it's a negative, it equals hot. Okay? So we know here that it's hard to start, so it has to have a hard ramp up. And then this thing here has to be higher than this thing, and it has to be higher by a whole lot, because you're measuring this to this. And if it's a negative, it equals hot. So your drawing should look something like this. All right? This reaction is easy to start, but gets only slightly warm during the reaction. Remember our ending, so the ending minus beginning, and if it's a negative, that means it's hot, right? So we've got to make it so that it is a negative. So this, from this, we have a short amount of, a little bit of a hump to get over, and then it doesn't have too much of a difference because it's only warm. We have, this reaction is hard to start, but slightly cold during the reaction. So again, remember ending minus beginning, and if it's a positive, it is cold. So we start here, and it's hard to start, so the hump has to be high, but the ending reaction has to be higher than this because we have to have a positive, right? So this has to be higher than this because when we subtract it, we have to get a positive out of it. And it's just slightly cold, so it doesn't have to be a big big difference. Okay, so this one is easy to start and gets very, very cold during the reaction. It has to have a high ending from here to here. So I guess it would have to look like that, because once it gets going, it just stays high. So again, remember our ending minus our beginning. If it's a positive, it's cold, and we get very cold. So the difference from this to this has to be great. So we're talking about the delta S for these, to see which one, the sign of delta S, and you're looking for chaos. So, and the chaos is determined whether, if you have gas, so the gas has most chaos, then comes liquid, then comes solid. And remember, the chaos meaning the amount of movement or interaction that the molecules would have. So if you have a chaos automatically, where if you have gas, it's automatically more chaotic. So in this particular case, our reactants have a gas molecule and these don't. So that automatically makes that our reactants are more chaotic. And according to have more entropy is what they call it. And so according to our book, that means that delta S is negative if our reactants have more chaos. So now we have gas in all of these, so they're all chaotic. But now we have to look at how many molecules are on each side. So we have a 2 plus 1 molecules here, 2 molecules here, so a 2 plus 1. So the reactant side has more molecules, which makes it a negative. Okay, so on the final one, we have a solid and an aqueous, aqueous, aqueous. Well, aqueous is more chaotic than our solids. We have actually 3 aqueous molecules here and only 1 aqueous molecule there. If it is in the reactant side, so the entropy, there's more entropy in the products, and that makes the sign of delta S as a positive. Okay. On your own problem 13.5, you determine the delta S of the following reaction, and use what you've just learned to calculate the delta S for the same reaction. Okay, so I think what we'll do is stop here, and I will go ahead and set it up and then come back to you. By the way, I just want you to know this whole problem was wrong. Our reaction here, we also know that the sum of delta S of the reactants. Okay, so we know that we're going to go here. This guy goes this way, and these guys go this way, and we're subtracting them. All right. Now, the other thing we have is, according to our tables, and I don't know, I think you can see that, we have our table for entropies, so that makes it really nice. We can just work from there. CaCO3 is here. It's a solid, so it's 92.9. We don't have any stoichiometric coefficients, so we just have to deal with what we're given, which is nice. And of course, this is more intense than the other one, so it's joules over moles times Kelvin. So we'll have a little bit more energy dispersion for that. All right, so our entropy for CaO, let's see if we can find it here. CaO as a solid is 38, so minus 38.2. And now we have to find CO2 minus CO2, which is a gas, minus 214. So remember, I'm minusing these two because they are the reactants and they need to be subtracted from the products. Okay, so when we get to that, when we add those together and subtract them, we get the delta S is minus 159.3 joules over moles times Kelvin, and that's your answer. That's it. They said it's 159. So they said it's negative 159. All right. 2CH4, which is a gas, plus O2, which is a gas, makes C2H6O, which is a liquid, plus H2O, which is also a liquid. All right, so remember in your reading, Gibbs energy, again, we're doing the same thing. Delta G is the sum of the delta G of the products minus the sum of the delta G of the reactant. So we continue to have that same pattern, at least, so that it helps prevent us from being totally frustrated. We also know in the Gibbs free energy that O2 is already formed, so we don't have to deal with it. Okay, so I've got my little delta G. It may be harder to see here, but here's my delta G, my standard free energy, right there. So I'm going to go ahead and I know my things go this way. Goes these two, right, products, and then this guy here. Because information C2H6O is minus 175, and H2O, and that's a liquid, so it's plus 237. Now I do my minus, and that is CH4, which is 2 times 50.8. And that's a negative. 2 times negative 50.8. All right, so now we're ready to go ahead and figure out. So our H2O is here, right? The other one is over there. And this is our positive. So when we start multiplying it out, we get minus 175. So we have a minus 237 minus 101.6. And so delta G should be minus 310.4 kilojoules. That's your answer right there. And they said, they also said minus 3.1 times 10 to the 2 kilojoules. Now the question is it spontaneous? So we're looking for spontaneous. Will it actually work? And the rule is if it's less than 0, then it's spontaneous. And this number here, negative 310, is less than 0. So the answer is yes, it's spontaneous.